Hello everyone, and welcome to today's STERIS Tech Talk on fundamentals of mathematical modeling and radiation validation processing. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is Zach Nutting, and I'm the Associate Product Manager for STERIS Applied Sterilization Technologies, and I'll be the host for today's event. Our presenter today is Spencer Mickum. Spencer Mickum has been with STERIS AST since May 2022 and has over 10 years of simulation and modeling experience in the radiation industry. As Principal Scientist for Simulation at STERIS AST, he is responsible for developing and supporting mathematical modeling activities related to radiation processing to schedule gamma source loadings, optimize product dose mapping, and improve qualification for gamma, electron beam, and X-ray irradiators. He has served as president of the Council on Ionizing Radiation Measurements and Standards and is currently chairman of the ANSI HPS N43.7 committee and a member of the ASTM E61 committee. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS Applied Sterilization Technologies YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Spencer to begin the presentation.
Thank you, Zach. That was a great introduction, and I'm excited to be here and be discussing the fundamentals of mathematical modeling for radiation processing today. Kicking things off, you can see on the left-hand side an image, a picture of me. I'm going to be discussing the brief agenda that's shown on the right-hand side here. So first, we're going to start off with data collection, and we'll go through virtualization of system parameters, and we'll spend some time on this. Second, we'll work through some of the model development. I'll show an example CAD model, and we can discuss in terms of what we're seeing. Third, we'll talk directly about radiation simulation and review some of the results. And fourth and finally, we'll see the post-processing applications where we're visualizing the radiation flow. Now, to start off with, mathematical modeling is a method that's used to simulate electronic photon transport. And so in a sense, we're using a method to be able to learn more about the situations that we deal with at STERIS every single day. In this sense, we're using it at STERIS AST in support of our design and validation activities. And the aim of this tech talk is to explain the fundamentals of modeling, the radiation simulation side of things, and the post-processing applications as they apply to the field of radiation processing. What we can see here on the right-hand side is an image that would show an example output from a radiation simulation model. Here we have the title being the RTC dose to plastic study using RayExpert, where RTC is the Radiation Technology Center at STERIS. And we'll get into a little bit more of this further on. Now, the mathematical modeling group at STERIS is responsible for developing and supporting mathematical activities related to radiation validation processing facilities globally. And it provides, as we can see here, optimized processes related to gamma source loadings, customer product dose mapping, qualification for gamma electron beam and X-ray irradiators, support for the design of new irradiation chambers, and the assessment of and potential impact of critical parameters on dose received by products. Now, thinking about how mathematical modeling is used, if we took a quick look at the image on the right, you could identify the region of highest dose around the upper edge of the simulated project, shown here by my cursor. And from the scale over here on the right, you could get an approximate for the dose uniformity from that range of calculated doses. Now, this data is fabricated dose from a two-sided X-ray irradiation using a polystyrene phantom. And as I mentioned, as we go through this presentation, we'll be delving further into this graphic. Instead of a brief outline, we'll go into a more in-depth outline that'll show steps that we're going to be taking today. In data collection, in the field of mathematical modeling, the common saying goes, garbage in equals garbage out. And that absolutely applies. And it means that without accurate and precise data input into the model, the results could be misleading or perhaps even wrong. So to combat against this, the mathematical modeling group at STERIS has a well-structured method towards data collection. And a priori information, as seen here on the first line, is relating specifically to the information that we can collect before we would go on site. The site visits are crucial towards ensuring that the model are an accurate representation of the treatment conditions for radiation processing. We would need to consider things like retrofits or unique scattering surfaces that may not be present in the a priori information. For model development, you can see that we've got computer-assisted design or CAD modeling of the irradiator site, as well as importing that CAD file into a radiation modeling tool. So model development really takes place in two parts. CAD modeling software is utilized to develop and maintain a library of each of the processing sites operated under STERIS AST, and then the CAD models are converted and imported into a radiation modeling software for simulation of radiation transport. So this includes several steps that are not limited to, but shown here: materials definition, setting up the interaction probabilities, and defining the radiation source. Now that the model is prepared, we move on to the radiation simulation, and there are several steps and decisions that must be taken to fully outline the scope of the simulation. Checking for errors is done with an overlapping test. Assigning the conditions for collection of the results is usually in line with dosimeter mapping, and we'll discuss that. And assigning the conditions of the results or when you can accept the uncertainty is how you would set your convergence criteria. And so that would be based off of a amount of computational time to use to get an output that is within reasonable uncertainty bounds. And now finally, we see that the simulation, with it being executed, we can now process the results. Post-processing takes up a large portion of this presentation, and that really shows one of the strengths of simulation, in that there are small changes that can be done rapidly in simulation that can be adjusted to learn a great deal about many features in the radiation processes. And so we'll only cover a subset of those today, but it's used to provide an insight into the fundamentals of mathematical modeling. Now, starting with data collection, shown here are several visual representations of the type of information that is being collected for mathematical modeling. And these are purely informational. They're not specific to any STERIS site. And they represent the a priori information that we can collect about a site. On the left, an engineering drawing of the site. And this graphic is not meant to be readable. It's just an illustration. And the form of the data that we can see when we're collecting information for mathematical modeling. Often engineering drawings such as these are decades old. So it really highlights the need to get that additional verification of the information to ensure accuracy. It's still a wonderful starting point to be able to have this information at the get-go. Next, the knowledge of the materials associated with the system infrastructure are critical to performing radiation simulation. So you can consider the variation of the densities that are shown right here. We've got wood. A common density for wood could be about half a gram per cc per cubic centimeter, and concrete is maybe around 2.5 grams per cc, and finally metals such as aluminum or even steel range between 2.5 upwards to 8 grams per cc. So if we were to think about these three materials and through the same thickness of each material, we'll say something like 10 centimeters, you could expect that from a like 100% of a 7 MeV X-ray spectra impinging on 10 centimeters of these materials, roughly 80% would get through if you were using wood in this simulation, and 40% would get through if you were using concrete. For something like aluminum, you would see more like 30%, and if it was steel, that goes down to about 3%. So this really shows you that appropriate assignment of materials to the components within simulation is especially important in order to produce an accurate result. On the right-hand side, we see the source definition, and the source definition refers to the gamma, electron, or X-ray radiation source. Here we're seeing an example of a gamma source. Defining the source describes the need to appropriately look at and locate where the product is going to be with relationship to the source, and understanding the physical spread of the source. So this could be a scanning extent for an accelerator, or as shown here, an activity distribution for the gamma irradiator. As shown in this image, the activity distribution is absolutely necessary to correctly predict the dose distribution within product. Without knowledge of the distribution, you wouldn't have an idea about that tight formation of sources up here on the top left. And if you didn't have this information, it would lead to a simulated output that wouldn't match the measured results. Additionally, you need to clearly define the energy and intensity of the radiation source, which we'll jump into more details about. Now that was all considering a priori information, and I have mentioned that the need to be on site and verify is crucial. On-site measurements, we have data being recorded with a software package that can directly connect to the laser rangefinder that we see down on the left-hand side of the screen. So gathering information in this way allows us to organize the information by individual sites, and the software allows you to integrate photos that are taken at the site, and you can overlay notes and graphics with dimensioning. So you can see here the example screenshot in the center of a site, and there's dimensions on the distances between the walls. There's associated pictures that have been embedded into this design drawing, and each one of those pictures, if selected, you can see that it would become larger, and you'll be able to get that information with those two measured geometries of a specific site. In addition to this, we also have the common tape measures and calipers and squares and the common tools that you would expect to be able to measure the site details. And all those measurements are recorded within the software that we use to be able to collect this data. So with the tools described so far and the methods that we've covered, we've been able to outline a facility. And that's everything that goes into building that model. And what we'll see next is the accumulation of all of these measurements into a CAD model. So here's an example of a completed site model, and I've created a GIF. Run through that right now. And while this is spinning around, I'll note that this model is not uniquely representative of any STERIS site, but we can see that the scanning end of the accelerator is installed flush with the internal wall. We can see that the ceiling has been removed from the model for clarity. The conveyance system directly surrounding the treatment area near the scan horn is included in the model, and the carrier, shown as we circled around it, is filled with a phantom material, and this would be similar to the material that is used during operational qualification or Q testing. Take one more circle around. But you can see all the different components that go into a model. Now our next step is to transition from the CAD modeling software that we were just visualizing to the radiation modeling software. As there are many options to choose from, I've listed a few here to give the idea that the approach that we're discussing here is not the only approach that can be taken. There's more possibilities. For our purposes, we have proceeded with integrating the CAD models developed by Autodesk Inventor with the CAD import features that are associated with the RayExpert code developed by TRAD. This process has been extremely effective in being able to retain the important information that we've walked through so far and translate that directly into our simulation models. Because again, as we've said at the beginning, garbage in is equal to garbage out, and we want to have the highest quality data going into our models. Thus, we have this connection. Continuing on to the next bullet point, we've identified our materials as described earlier, and now we have to define them within the simulation software. So within the software, we have a comprehensive database of reference materials to choose from. This is the case specifically for RayExpert and might not with other possibilities. This is convenient, as there's this reference material database to choose from, and this often meets the needs for the radiation systems that we work with. There is a feature to create your own materials, though, in order to provide you the flexibility for variations of materials or for materials that aren't defined in this software database, which does come up and quite frequently too. So being able to have the capability to save those materials in a reference database is beneficial, because then you're allowed to reuse them with ease. Subsequently, we now need to define the radiation source. And this bullet point highlights the range of possibilities that come when defining a source. We can see that there are options that show the amount of rigor to undertake. And a good approach would be to model a monoenergetic source, a source with a single energy, with isotropic emission for gamma, and you can see the slash there for parallel being some type of an accelerator-based system, and zero self-shielding, where zero self-shielding we're referring to the interaction of source particles passing through, attenuating or scattering with the physical source infrastructure. This could be physical cobalt, or the cladding surrounding the sources in the cobalt system, or gamma, or structural materials of the scan horn itself, or a accelerator-based or electron or X-ray source system. And this is good. This is denoted as good because the results of such a simulation will provide results that are able to trend correctly with measurement, but not precisely reproduce them. And so that's a significant difference. So looking at better is to establish the appropriate energy and angular distributions of the source and add in those source geometry and materials that we just touched on. If you establish a relationship with the source manufacturer, however, this, which would be based on a mutual benefit between shared information, allows the simulation process to capture variations of the source. With the better approach, you could expect to be able to match results, but it might not be repeatable. And that is because the sources will change over time, and even minute changes can impact the simulation results. So here, that relationship with the source manufacturer is something that really separates a simulation provider being able to have that information and produce a repeatable foundation for simulation that can be used for time forward. Okay, next we have several slides with graphics, courtesy of TRAD, the maker of RayExpert. And these graphics showcase the data collection experience that's derived with radiation simulation. You can see in this first graphic, this depicts an example single pass cobalt irradiator. A cross-sectional view on the right-hand side shows how this dose distribution would be varied based on the position within the bunker. And from this, you can infer that the accumulated dose would be the summation of all of these parts. It's worth noting that there are some significant differences between the center points, between the edges, and especially between the points along the left-hand side. I'll use my cursor now, we can see the points along the left-hand side and the center points and the edges. And here we come to a question about simulation from the standpoint of computational capacity is benefited from being able to accumulate the dose from all these individual substeps. And this would be what we would call a dynamic representation of simulation, something where we're reproducing the actual motion that a product or a carrier takes within an irradiator. Okay, next, let's take a look at the business end of an X-ray accelerator. This model shows how you can overlay the dose deposited within product directly over the CAD model. And this allows for a higher understanding of the control that goes into the dose delivered to a product. You can imagine being able to have this information and uniquely identify beam size, scanning parameters, and quickly identify what that would relate to given your scale on the right-hand side with how your dose uniformity would change and be adjusted given those parameters changing. Being able to do this and integrate this process would massively support the existing processes that go on every day right now with reliance upon dosimetry measurements as well as experience. Finally, we'll look at the individual electron tracks going through an e-beam processing facility. And this type of information is helpful. It can be used to visualize the penetration depth of those electrons and understand the dose variation that might be present given the changing product packaging size. And once benchmarked, you can even anticipate the change in dose distribution due to changes in the product packaging that's shown here left to right with alternate materials being irradiated under otherwise similar conditions. So we've made it halfway through our outline from the beginning of the presentation, and it's clear that a tremendous amount of work goes into constructing a firm foundation upon which to perform simulation. A few steps remain before we can really get the fruits out of this labor. And the first would be making sure that there are no geometry errors within the simulation. And what this looks like is that the model would be checked within the radiation software package. And these checks consist of the areas where the geometries of two different materials may be unexpectedly overlapping, as shown in the first image here on the top. This orange area highlighting the overlap itself. Now, being able to quickly remove these overlaps and correct for them is essential to being able to have a rapid process where simulation can be used effectively. And this is also integral to being able to make sure that the CAD models that you import into your software are representative of what is being actually sterilized. And given this detail, this level of accuracy that we're able to see precisely where the overlaps are, I will make a note here about defeaturing, which is you can consider that there will be some features within products and systems that are not necessarily impactful from a radiation dose perspective, but are certainly impactful from a mechanical design perspective. So routinely, components that are not included in radiation models, such as fasteners or screws, small engineering features, control system switches, and so on, these things would be excluded. The level of detail required for an accurate simulation representation will always be weighed against the computational cost and the effort required to define each and every detail and generate appropriate models that consist of all those details. So compromises are made when the calculated results are not impacted. Following this setup step, the dosimetry can be replicated in simulation. Here we can see on the image on the right-hand side, what we have is a dosimetry system that's simulated to mirror positioning from actual measurements. And this image shows the array of dosimeters placed evenly across the surface of the phantom within the carrier, and such simulated mapping can be directly compared against measurement for benchmarking the simulated model. Now, this is very powerful because once we've benchmarked the simulation model, that allows for interpolation beyond the set measurement points shown. And if you can look down here in the final image on the bottom, what we have now is a quarter section view of the phantom that was irradiated has been isolated to fully visualize the dose penetration and the distribution within the interior. And this comprehensive information, once fully benchmarked, is extremely valuable, especially considering that here we're just looking at a homogeneous phantom. But as we go deeper into products with specific complex geometries, identifying the integrate features within the product and localizing where those maximums are, where those minimums are, and being able to understand where where dosimetry needs to be placed on product to understand the full dose uniformity is a very powerful tool, especially considering the amount of work that goes into building this model. Now we can make small changes and tweaks to it and be able to get a lot of new and very valuable information out of it. So finally, the convergence criteria, which we've touched on once, must be established. And what this is it's relating an acceptable level of uncertainty in the simulated results to the computational costs that are associated with achieving it. This would be realized from something like a length of time. How long are you going to be running your CPUs or your computer processing units? Or how many particles are you going to be run? These are synonymous, giving a number of particles run at a set number of time. Or even setting a specific uncertainty to achieve and having an unknown number of particles or CPU time to run until that uncertainty is achieved. All of these different convergence criteria are appropriate given the application and the level of uncertainty needed for the results. So graphical representations of the energy levels of the simulated particles can be shown on the next slide. And what we're looking at here is how the element, which we see FF1 relating to front face 1, is shown in the table at the top. And we can see in real time how the flux or the dose within that element is changing, as well as the sigma or the uncertainty percentage is changing as well. These representations help begin to visualize how the results are being collected as a function of time and quickly identify if the time is what is being expected. So showing the change in the particle flux within the defined dosimeter locations, we can see the sigma value will reduce over time until one of the convergence criteria is met. On the bottom left-hand side, we have a graphical plot showing the flux values versus energy. The energy levels of the simulated particles, you can see, are varied between the three sets of data, with the three sets being the front face, the center face, and the back face, and being able to visualize those three different energies penetrating through and changing. And then on the right-hand side, what we're seeing is the convergence of these values. At the beginning, the shot number being very low, you can see there's a large disparity between all the different points. But over time, as the number of particles run increases, we see a convergence of all those into a fine bunching that shows that we're achieving convergence within our results. So now we've collected our information, and we've developed our model, and we've initiated the radiation simulation. So the question is, now what? Because to this point, we haven't gotten anything out of it. We've just put a lot into it. So post-processing applications is here to describe the different techniques where mathematical modeling is being used, and albeit not fully comprehensive list, show a couple of examples about how this can be used in the future. This first set will be touched on each with its own slide, but the first would be showing max dose and min dose and determining where they are in a product, as well as product dose mapping. What we'll see here is the identification of the min dose and the max dose locations. From the example on the left, we've performed the simulation and highlighted with red and blue circle, with red square and blue circle, where those max locations are. And we can quickly identify this from the results, and we can also go through and fine tune where the dosimeter placements would need to be able to capture these locations. Tracking backwards, our second bullet point now is dosimeter optimization studies. And this is something where being able to understand the effort required for placing a dosimeter is extremely important for routine processes. It helps understand the sensitivity involved, and we can get an idea about the effect of what the dosimeter result would be if the product density was changed, if there were local density changes, or if the gap size between product containers being irradiated was increased or decreased. Scaling forward, we have an example plot that shows for this specific example that within a certain range of distance, the centimeters scale on the bottom showing between -3 to 6 centimeters, we have a certain range of dosimeter responses in terms of grays per particle that are within plus or minus 2 sigma that would be related to the uncertainty of the detector itself. So a dosimeter that's placed upon product would have a certain inherent uncertainty to it. And from simulation, we can see that moving that individual dosimeter to the left and the right by this distance of centimeters would have a low impact because it would all be recorded within the uncertainty bars. However, we can also visualize that on the left-hand side of this image, there seems to be a rather steep gradient. And this gradient shows that as we move into the negative values, we're really approaching an area of high change. And so having the dosimeter placed in this location is much less likely to be able to have reproducible results than as we see moving to the right and going into positive numbers, we see a nice flat response and then a much less steep, much more gradual incline in the change. And so using this data, we can interpret what the appropriate dosimeter location should be, and additionally be able to understand the impact if they were moved. I'll show here that although it's hard to see, the simulation uncertainty is overlaid within each one of these bullet points, shown as the small bars on the top and the bottom of each of these points. Cycling back to our last bullet point, the product process capability studies can be done, and this is a unique feature for being able to rapidly perform process capability studies for customers' product. New product development can also have simulation incorporated into it to ensure that products coming to sterilization prior to going to market are already validated as being process capable. There are product optimization studies, and typically product optimization and packaging optimization are some of the key features where simulation can really be beneficial. I think this would be noteworthy to say that low-hanging fruit would be something like being able to put a product through simulation and changing the orientation, and being able to understand how a slight change in orientation may affect the dose uniformity and affect the min and maxes, and perhaps even affect process capability. That, I think, will be a very easily, quickly adopted use of simulation as more of these other post-processing applications are built out. Now, finally, we have an example here about the studies on switching radiation modalities. And being able to perform these studies is also very beneficial towards the evolving radiation processing field. We're going to cycle through the slides we just viewed and see our final example, which is an example about the optimization within uniformity for a specific product. Here we can see on the left-hand side that a product uniformity would be 1.20 for routine processing. And perhaps without simulation, it might not have been recognized that a slight change in the orientation, where we can see from left to right, this packaging has been tilted on its side, we find that there's actually a significant improvement in the dose uniformity achieved. Now, being able to do this or a number of other iterated orientations is extremely important to being able to optimize processes. And that is where simulation really has its strength, because there can be infinite variation of different orientations for product packaging. And as long as those operate within the bounds of what is realistic to be able to be fabricated and designed and made, then this provides a way of making sure that the best possible outcome is achieved with radiation processing. A very high strength when it comes to using mathematical modeling within the field of radiation processing. Okay, we've had our same 4 bullet points on top: collected our information, developed our model, initiated radiation simulation. Now what? And we have 3 new bullet points here to review. And with these, we'll just be talking through them, and we'll see that the variant studies for the first one is important for the 2 pictures over on the right. Variant studies to optimize installation qualification or operational qualification, known as IQ/OQ, and troubleshooting reasons for nonconformances is another reason for mathematical modeling being used. And shown on the right, what we can see is variation of the scan width. And the scan width for an accelerator can be changed, and the impact that that would have on dose uniformity is a process going through multiple tests and myriad dosimeter readings. The variation that can be performed with simulation, again, iteratively going between many different examples of different scanning widths, we're able to see the impact that this would have on product dose distribution. This is extremely powerful, especially considering the impact that such changes to the system, to the source, have on the dose uniformity. So especially considering the impact of the scan width, being able to make these studies in concurrence with operational qualification testing allows a large component of the testing to be not necessary and optimization to be determined. Furthermore, the non-conformances is a way of being able to selectively remove pieces and parts of a benchmark simulation model and identify the impact that each one of those parts would have. And considering that impact, be able to try and relate that to any changes or any non-conformances that are occurring within routine processes. By this way, it's possible to determine the impact that something, perhaps a dosimeter falling, perhaps a piece of the materials that are used to suspend the product are being incorrectly moved in place, and different examples that could be gone through with simulation to identify the impact that they would have. Next bullet point shows that optimization studies on system geometries to improve throughput or dose uniformity. And this optimization studies is an example that automation is being embraced to standardize processes. And questions, while this is occurring, have arisen on how significant changes to system geometries will impact dose delivery. So perhaps, for example, a site transport pallet needs a modification that would allow it to integrate within the proposed automation strategy. In this case, simulation may be used to uniquely identify the impact that the changes in the geometry on that pallet would have and identify any potential concerns before any site changes are ever made. Finally, the last bullet shows the supportive design of new irradiation chambers. And this is something that has been already used and historically has done an excellent job being able to plan and anticipate and be able to place radiation safety when designing facilities. So this shows that being able to determine the thickness of walls or being able to check compliance with the existing radiation protection criteria, and also being able to do all of this before the time and resources are put into building new infrastructures. So as I mentioned earlier, it was a short overview of some of the different post-processing applications, by no means comprehensive. Here we can see another example where we're going to visualize the transport of radiation through the product. And again, this ability to characterize the radiation transport will be very helpful in identifying where the locations within the product and where the dose distribution is going. As we could see from the video that we just saw, there's a pretty clear note that the dose at the very top, if we review this again, seems to be coming in much, much quicker than the dose at the bottom. Visualization of this distribution is helpful for identifying perhaps changes to the processing routine, or being able to understand dosimeter response and be able to use and integrate that information into bettering routine processes and the services provided by STERIS. Now, in terms of final remarks, mentioned several times throughout this presentation benchmarking. And I wanted to make a quick note that to ensure functionality of mathematical modeling, validation and benchmarking is required. There has been guidance from the Food and Drug Administration, the FDA, on specifically what can be done in terms of medical devices to be able to appropriately benchmark simulations. For the example shown here, there are standards. In this case, we're looking at the standard ISO ASTM document 51649 that will describe previously validated measurements within a specific material. Now, using these as benchmarks to be able to improve confidence that simulations are working the way they should is really a first step to being able to make sure that the model can be on a strong foundation and be used. The next step, of course, is using dosimetry and ensuring that your models would be checked against these measurements. And so here we're seeing examples of several different curves through different plastics and with different standardized depths, and being able to reproduce this with simulation, as we see here on the right-hand side image. Now, is mathematical modeling being used already? I've mentioned previously that it currently has been used, and it is being used currently. There are several documents, again, by no means a comprehensive list, but just a selection to be used to visualize some of the ongoing work and some of the previous work. The first being the ASTM E2232 standard guide for selection and use of mathematical methods for calculating absorbed dose in radiation processing applications. The second, a document that outlines the work for the EGGS NRC toolkit for Monte Carlo simulation, EGS NRC. And finally, a paper by Josef Mittendorfer about the complexity of photon fields in medical devices with heterogeneous density distributions. These different references can be viewed and read up on for some of the current processes going through with mathematical modeling. And the final question to ask for today is, we've spent a lot of time looking at the system design and OQ, but what would be the next step? And that would be incorporating customer products. In this case, we anticipate a future talk to be able to describe exactly what this process looks like. In short, in brief right now, it would be critical to be able to have a very good understanding of the product geometry and map it according to that. And in this case, we're showing here for an example container, being able to use something that is referred to as tetrahedral meshing, where the meshes conform specifically to the dimensions of the product, and being able to use that tetrahedral meshing to reproduce, to simulate the product within our radiation simulation. Again, a powerful tool that can be integrated and be able to help make sure that the simulations provide an accurate and appropriate result. With that, I will thank you for your attendance, and I will be happy to address any questions. Thank you again.
Thank you all for attending today's STERIS Tech Talk. We appreciate you taking the time to learn with us and hope you found this session beneficial. You can find recordings of today's Tech Talk and all previous webinars on the STERIS AST YouTube channel. Thanks again. This concludes the webinar.